Yeah, so we've got the notes for section 2, which deals with the mean value theorem. So here we've got the mean value theorem itself. That says if y equals f of x is continuous at every point of the closed interval a, b, remember brackets mean the endpoints are included, and differentiable at every point on its interior a to b, so endpoints not included, then there's at least one point c in that interval, which the instantaneous rate of change equals the mean rate of change. So this is your formula. So remember the derivative is instantaneous, so f prime of c is equal to f of b minus f of a over b minus a. So example 1 here says show that the function f of x equals x squared satisfies the hypotheses of the mean value theorem on the interval 0 to 2, and then find a solution to the equation. So we'll look at the graph. So 1, 2. So when x is 0, y is 0. When x is 2, the function has a value of 4. So there's the graph of x squared between 0 and 2. So continuous, check. Differentiable, no corners, no cusps, so also differentiable. So I can actually work this problem out. So this point appears at 2, 4. So f prime is the derivative, which is 2x. So f prime of c is just 2c. And that's going to equal f of b minus f of a. Now, this is the slope equation. F of b and f of a are y2 and y1. B and a are x2 and x1. So this would become 4 minus 0 over 2 minus 0. So you would have 2c is equal to 2, so c equals 1. So at the point 1, 1, if I plug 1 back into my equation, the tangent line will have the exact same slope as the secant line. So the secant line is the one that just connects the two endpoints. The tangent line actually touches the curve at a single point. So the mean value theorem says assuming the function is continuous and differentiable, there is always some tangent line that has the same slope as the secant line. So down here in example 2, it says explain why each of the following functions fails to satisfy the condition. So we're actually going to look at the graph for each of these. So for this one, if you work the graph out, it looks like this. So this is not differentiable, is the problem, because of that corner. Down here, as piecewise, so there's x equals 1. So at x equals 1, I actually have to use this bottom equation, which gives me a y value of 2. But that's it, because this graph would normally go right. So now I have to switch to this one. So when x is 1 in this equation, I get 4. But that's going to be an open circle because I can't actually use that value. When x is 0, I would get 3. And when x is negative 1, I would get 2. So this graph is not continuous. So I have to lift my pencil to jump from there to there. Okay, so example 3 says let f of x equal to the square root of 1 minus x squared. Point A is negative 1, comma, so this is just the y value when x is negative 1. B is 1, comma, f of 1. Find the tangent to f in the interval negative 1 to positive 1 that's parallel to the secant. So the first thing I need to do is actually figure out where points A and B are. So A lies at negative 1, comma, whatever I get when I plug negative 1 into this equation. So if I plug negative 1 in, I get negative 1 squared, which is 1. Then I have 1 minus 1, which is 0. The square root of 0 is 0. Point B lies at 1, comma. So if I plug 1 in, 1 squared is 1. 1 minus 1 is 0. So that's the thing. So I can find the slope between A and B. So y minus y over x minus x. This whole thing is just 0. So what I want to do is find the tangent line that has the same slope as this. Now to write the tangent line, I need 3 pieces of information. I need the slope, I need the x value, and the y value. So I need to know first where this function's derivative is equal to 0. So we're going to rewrite f of x real fast to make power rule easier to handle. So remember, square root is the same thing as a half power. So f prime, the derivative, exponent comes out front, leave the inside alone, count down by 1, and then multiply by the derivative of the inside. So this would be negative x times 1 minus x squared to the negative half. So I'm actually going to rewrite this. That negative half is a square root on the bottom of the fraction. So this is the equation for the derivative. I need to know where is it equal to that slope, so equals 0. Now the trick here is if you have a fraction, the only way a fraction is 0 is if the numerator is 0. So I can just worry about this, which means when x is 0, the derivative has a slope of 0. So I have my x value. I have my m value. It's right there. I just need my y value. So to find the y value, I plug x into my original equation. So if I do that, I get 0 squared is 0, 1 minus 0 is 1, the square root of 1 is 1. So my equation would be y equals mx minus x1 plus y1. So there is your tangent line that has the same slope as that, parallel to the secant, has identical slopes. Okay, so example 4 says if a car accelerates from zero takes 8 seconds to go 352 feet. Its average velocity for the 8 seconds is 44 feet per second, so that's 352 divided by 8. Is there some point at which the speedometer must have read 30 miles per hour? Yes. The speed is continuous. You can't skip values. And differentiable, you wouldn't have any corners or cusps, which means, the speedometer, which measures instantaneous, must equal the average. Okay, so increasing, decreasing functions. So let f be a function defined on the interval I, and let x1 and x2 be any 2 points in that interval. F increases on I if x1 is less than x2, if f of x1 is less than f of x2, which means the y value that corresponds to x1 is less than the y value that corresponds to x2. And x2 is to the right of x1. Essentially means the graph has to rise, x1 to x2. Decreasing, x1 less than x2, so I start here at x1, here's x2. If the first y value is more than the second, so the graph has to fall as it goes towards x2. So it's kind of literally just the definition of increasing and decreasing. So your other thing here, so you also can define it in terms of the derivative. Let f be continuous on the interval a to b and differentiable on the interior. If f prime is greater than 0, so the slope is positive, then the function increases because this positive slope means going up. If the derivative is less than 0, so it's negative slope, the graph is decreasing. So it says determine where the function y equals x squared is increasing or decreasing. So we can just do this by looking at the graph. So the graph of y equals x squared looks like this. So this function is increasing on the interval 0 to infinity. Starting here, it's rising. It is decreasing on the interval negative infinity to 0. Now you have to be careful with increasing, decreasing, because you're always actually reading left to right. You don't start at the lowest point and go, oh, it's increasing on both sides. You're reading the graph left to right. So it's increasing starting at 0 going up, or going right forever. It's decreasing, falling, starting at negative infinity, moving towards 0. Yeah. So example 6, where is the function x cubed minus 4x increasing, and where is it decreasing? So once again, we're just going to look at our graph. I don't know why I rewrote the equation. So let's see here, x cubed minus 4x. Draw it. So that looks something like, let's see here. Let's find our 0. We'll use my calculator to find my zeros first to kind of give us a place. Looks like we got a 0 at 2. So we know we go through that point, and that point. Negative 2, 0, 2. Looks like we have a maximum at negative 1, comma 3. So right there. We have a minimum at positive 1. Max. That's about, yeah. So that point is actually negative 1.15, comma 3.08. And then, whoops, let's find the minimum. G-solve minimum is down here at 1.15, comma, negative 3.07. So the graph does something like that. Okay, so we'll read from left to right. So for increasing, we start at negative infinity, and we increase until we reach negative 1.15. Then we decrease, decrease, decrease until we hit this point. So joined with, starting at 1.5, going up to positive infinity, which means the decreasing portion is just the part in the middle, from there to there. That's where the graph is falling. So from negative 1.15 up to positive 1.15. Remember, the symbol here is the union. It joins two inequalities, or two intervals. Okay, other consequences. If your derivative is 0, you have a constant function, meaning it's a flat, straight line. Functions with the same derivative, but are differ by a constant. So if f prime of x equals g prime of x at each point on the interval I, there's some constant c such that this is true for all x and I, which means so this would differ by a constant. So like x squared, so here. So for example, x squared and x squared plus 2, they both have the same derivative. The derivative of this is 2x, the derivative of this is 2x. So f prime is equal to g prime, and they differ by some constant. But the thing is, there's an infinite number of these. I could put 3 or 4 or 5 or negative 2 or negative 3 or negative 4. So this c value depends on some given value that it goes through. So example 7 here says find the function f of x whose derivative is sine and whose graph passes the point 0, 2. So we can actually look up what function has a derivative sine. The function whose derivative is sine is actually the negative cosine. But I need to put a plus c on there because I have this initial point. So the point 0, 2 gives me an x value and an f of x value, or a y value. So this equation, cosine of 0 plus c, has to be true. So the cosine of 0 is 1, so we have that. So c is equal to 3. So the equation is f of x is equal to the negative cosine of x plus 3. So this function will have a derivative that's equal to sine and will also pass through that point. Now, any function that has negative cosine x will have a derivative of sine, but in order to get to pass through 0, 2, I need that plus 3 at the end. If that had been a different point, that would be a different value for c. Okay, so antiderivative, a function capital F of x is an antiderivative of a function lowercase f of x if f prime of x, capital F, is equal to f of x. So that's what we did here. So this function is f of x. The negative cosine of x would be the capital F of x, the antiderivative. The process of finding an antiderivative is referred to as antidifferentiation. So essentially, we're working backwards. Okay, so 8, find the velocity and position functions of a body falling freely from height 0 meters under each of the following sets of conditions. Acceleration is 9.8 meters per second squared, and the body falls from rest. So it gives me A is negative 9.8. So the velocity is the antiderivative of this. So instead of counting down exponents, I need to count up. So that would give me a t. Now this would be plus some constant that I need to figure out. I do know the body falls from rest, so I know that 0 is equal to negative 9.8 times 0 plus c. So when time is 0, the thing isn't moving. So in this case, c is 0. So my velocity equation is just negative 9.8 t. Then to get the position equation, that's the antiderivative again. So this negative 9.8, this becomes a t squared. Count up. Now the problem is that's not negative 9.8 anymore because the derivative has to be 9.8. And when this 2 comes out front, there has to be a 4.9 out front. And this is plus some constant, c again. Now in this case, we don't know exactly where it is, so, from a height of 0 meters. So we know that when t is 0, s is 0. So 0 equals negative 4.9 t squared, 0 squared, plus c, so 0 equals c again. So this just becomes negative 4.9 t squared. So remember, when you take a derivative, this multiplies out front. So when you do an antiderivative, it's the opposite, so it would divide up. So if I have to put a 2 up here, I have to divide that by 2. So that's why it's negative 4.9. All right, so this problem starts the same way. So there's our A equation. So then V is equal to negative 9.8 t plus some constant. Now in this case, it's propelled downward with an initial velocity of 1 meter per second. So I know that 1 equals negative 9.8, t is 0, plus c. So in this case, downward makes it negative 1. So c is negative 1. So my velocity equation is negative 9.8 t minus 1. So now I need to antiderivative again to get the position equation. So I count the exponent up, so divide that by 2, so negative 4.9. Now this doesn't have a t, so when I do the antiderivative, it becomes t to the first, negative 1 divided by 1 is 1, and then some plus c drops on the end. Now this object falls from a height of 0 meters, so I know that when t is 0, s is 0. So 0 equals negative 4.9 times 0 squared, minus 1 times 0, plus c, so c is just equal to 0. So my s equation is actually negative 4.9 t squared minus t. So there's the position equation, assuming we have initial velocity 1 versus from rest initial velocity 0. But that brings us to the end of this section.